All right. Hey, Daniel. We are on 23. This is on the review. We're going over these questions. Do you remember what the name of this dead guy is called? What was his last name? What was this? What's this? How do you pronounce this word? Shh. How do you pronounce that? L'Hopital. Whatever. All right. So we need to plug in the number into here and figure out what form he is, okay? And I told you this yesterday that this was a typo. This should be 0, so fix him. 23, all right? Did we get that far? I erased a little bit. If we plug 0 in, e to the 2 times 0 power is 1. 1 minus 1 is 0. If I do tangent of 0 on your unit circle, what's tangent of 0? 0. That is one of the forms, so 0 over 0. Got it? Okay. So what do we do now instead? Take the derivative. Okay. The derivative of e to the 2x. E to the 2x, but times 2. So I'm going to put the 2 out in front. What's the derivative of negative 1? Gone. Okay. What's the derivative of tangent?
Cosine of x.
What?
1 over cosine of x squared.
Like secant squared, right? X. But secant is 1 over cosine squared. Okay, so here's what I'm going to do. I'm going to keep flip him. Can I do that? And flip him to the top. So now I have 2e to the 2x times cosine squared x. Can I do that? You see how what I just did? I moved him to the top. Okay, now we're doing the limit as x goes to 0 of that. Okay, beautiful. Now we're going to plug stuff in. If I plug in 0, right? 2 times 0 is 0. What's e to the 0 power? 1. So I have 2 times 1 times, okay, what's cosine of 0? Look on your unit circle. What's cosine of 0? 1, but then I have to take 1 squared, right, because it's cosine squared. So 1 squared is 1. So my limit is 2. Hey, that worked out nice. We went from something that we couldn't do to taking the derivative, and it worked out. So, beautiful. Okay, happy with that? Something like that?
I don't like that smell.
I'm sorry.
I don't know either.
Okay, next. Oh, this one's fun. If I plug in infinity, what's 2 times infinity minus 5? Still a really big number, infinity, right? What's infinity times 3 plus 7? Still a really big number. Is that one of the forms that we can do?
Yeah.
Infinity over infinity? Yep. So I'm going to do what? This one comes out nice. What's the derivative of the top?
X minus 2.
2. What's the derivative of the bottom?
3.
And I'm finding the limit as x goes to infinity. How do I do that when there's no x's left? It's like I want to plug in infinity.
It's a straight line.
Yeah, I want to plug in infinity. Where do I plug it into?
You don't need to.
You don't need to. What's the limit?
2/3.
Just 2/3, right? Yeah. Also, do you guys remember when we did n and m? That thing?
M&M's.
N and m. N is the degree of the numerator. M is the degree of the denominator. Since they're both the same, we take the leading coefficient, 2 over 3. Yeah? Okay. 25. If I plug in 0, what's tangent of 0?
Didn't we just do that?
0? Isn't it?
0, 0.
Tangent of 0 is 0. If I plug in 0 on the bottom, it's just 0. So I have 0 over 0. Now what?
What's the derivative of tangent?
What's the derivative of tangent?
1 over cosine of x.
Is secant squared. X, which is 1 over cosine. We'll get to that. Okay. Over, what's the derivative of x?
1.
1. Okay. So I'm going to switch that secant squared to 1 over cosine squared. And I don't really need this 1 on the bottom because he's just taking up space, right? Now I plug 0 in. What's cosine of 0? 1. And if I square that, it is 1. And 1 over 1 is 1. Derivative. Okay, so if you end up with one of those little weird things happening, just know that you can take the derivative of the top, derivative of the bottom, and then plug your things in. Got it? All right, should we work backwards and do some related rates then next? Or do you want to go back to the top? Let's do related rates. Let's start with, should we start with 19 or you want to go 21 first? 19. All right, surface area. It's highlighted. The edges of a cube. I'm going to guess that we're doing surface area of a cube. True? Cube. I'm going to draw a dang picture. there. Look at that. The edges of a cube are expanding at a rate of 8 centimeters per second. Okay, let's label this cube. What do you want to call the edges?
ABCD.
Yeah, but we don't need A, B, C, D because they're all the same.
E for X.
No, because E is a number.
X.
Let's call them X. So this is X, and this is X, and this is X. It's X by X by X, right? Okay. Okay, and the edges are expanding at a rate of 8. What does that mean?
R equals 8.
Well, what is the rate of this side span expanding?
DX.
dx dt, right? If we call it x, dx dt is the rate at which it expands, right? And that is 8. How fast is the surface area changing? What is the rate of change of surface area called?
Rate of change of surface area.
Is that like D or DT? Or DA?
D, I'm going to go dsa dt. That sounds really weird, but I'll go dsa dt. The rate of the surface area changing with respect to time. When each edge is 6.5. So what is 6.5?
That's R edge. X.
X. That's what we've called him.
Oh.
Okay, the only thing that we're missing is the equation. And what are we doing an equation for? Surface area of a cube. Surface area is the area of all of the surfaces. What's the area of this front surface? X squared. What's the area of this side surface? X squared. What's the area of this top surface? Are they all x squared?
Yeah.
Yes, and there are 6 of them. So what's the surface area?
X squared.
6x squared, or x squared times 6. Now what do I do?
Derivative.
Derivative. What's the derivative of surface area?
12x.
What?
12.
What? Oh, what's the derivative of SA?
Oh, SA dx. Or dt.
dsa dt. Right? Okay, that is 12x. And then what? Nope. What am I missing?
Oh, ds a dt. You
No.
plug in 6d.
No.
times 5.
dx dt. We need a dx dt on the end of it, right? Yep, because we're not taking the derivative with respect to x anymore. It's derivative with respect to t. All right, we are trying to find this guy. And we are plugging in numbers. We're plugging in 6.5 here. And we are plugging 8 in there. Well, whatever that comes out to be. What's 12 times 6.5 times 8? The rate of change of the surface area with respect to time is, I don't know, whatever that is. 96 times 6.5.
624.
624? What per what?
Centimeters squared a second.
What?
Centimeters squared.
Centimeters squared, because it's area, right? Per second?
Yep.
Second. That is the rate of expansion. That's pretty decent size, actually, honestly.
How long is a fortnight?
Really tell Mrs. Commissioner where you find your calculator at.
It was in the corner of the civics room, just sitting there.
Why? Were you using it in civics?
It's by the way he said so.
Interesting.
I looked through it.
I don't know.
I sit over near there, but I wasn't using it.
Okay.
Must have threw it.
Okay. 20. An accident at an oil drilling platform is causing a circular oil slick. Here's my circle.
That doesn't sound OSHA.
Whoop. There's my circle. I drew it like that because, instead of drawing a circle, because we're talking about the oil slick having a thickness. So now it's no longer a circle, it is a what?
Cylinder.
It's a cylinder. Now, I'm over-exaggerating the height. Like, that's way exaggerated, okay? So 0.08 is the thickness of it. Okay. And when the radius is 750 feet, 750, the radius of the slick is increasing at the rate of 0.5 feet per minute. Okay. All right, we got a lot of things going on here. What is, let's write our given information down. What is 0.08?
That's the height.
That's the height. 0.08. Okay, when the radius is 750, radius equals 750. The radius is increasing at a rate of blah, 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 right? 0.5. The radius is increasing at a rate. DRDT. At what rate is the oil flowing from the site of the accident? What does that even mean? At what rate in, okay, the units will help me, in cubic feet per minute. What is cubic feet? Volume. So we're looking for the volume of a cylinder. Yeah, find volume of a cylinder. The area of the base times the height, right? Area of a circle is pi r squared times the height, h. So pi r squared. I don't know why I put so much room in there, but anyway, that's okay. Volume, pi r squared h. What are we trying to find? At what rate is the oil flowing from the accident? So we're trying to find
dVdt.
We're trying to find the rate of the volume. Yep, dV dt. Okay. Whoop. I'm gonna go down here. Derivative. Oh, hold on just a second. Hold on just a second. One more thing.
Oh my goodness. What?
One more thing. Before I find the derivative, this is gonna be really exciting. Is the volume gonna change
No.
as it slicks out?
No.
Yeah, this cylinder will get bigger. The volume is going to get bigger, right? Okay. Will the radius get bigger? Or will the radius change as it gets out, as it slicks out? Will the height change?
Yeah, no. Yeah, it could. No.
It's going to keep going out. The height's going to stay the same, right? As it slicks out.
But what?
Yeah, the height's going to stay 0.8.
According to.
Well, it can't go up any higher.
Well, we know it is.
Unless it's confined and it starts working its way up
Okay,
that
but how
container.
did it get to that height in the begin with?
Well, because it has to have a certain height.
Surface tension.
Yeah,
Well,
like something to do with that, right?
Something in waves, you know, like the height will fluctuate.
Well, yes, if somebody disrupts the
Of
slick.
course.
And what
But
if there's
here-
But it's
in
gonna
this
stay
circumstance,
it's
the
gonna stay
constant.
0.08 feet thick, which is like really tiny, and it's just gonna keep going out at that height. So the height is not going to change, which means, what?
It's a constant.
It's a constant, which
So you
means
plug that bad boy
we
in.
plug it in before we take the derivative, right? 0.08 stays like that, right? Okay, so I'm gonna put him in front, 0.08. And now we don't have a height variable anymore. That's kind of fancy. So, guess what?
Chicken water.
We don't have to use the
Product rule.
product rule because we only have one variable on the right side, right? It's just
Oh.
radius. Yeah? Okay, what's the derivative of V?
0.116 pi r.
What?
Is this?
dV dt?
Yeah.
Okay, you're doing the other side. Pull the 2 down in front. Billy says 0.16 pi r. And then what?
DR.
dRdt. Yep. Now we plug stuff in. We're trying to find dV dt, right? Equals, I'm just going to do this. R is 750. Are these all in feet, by the way? I really hope so. Thanks.
Well,
Nah.
yeah,
I think they are in feet,
you know,
actually.
something.
That's why it's 0.08 feet thick. That would be really mean if they did that to us. Okay, multiply. Half of 750 is 375, if you want to do that.
Wow. 375.
Times 0.16 times pi.
188.5
188.5. What per what?
cubic feet per minute.
Cubic feet per minute. Perfect. That's the rate that the volume is changing. Wonderful.
Honestly, this smell makes me nauseous.
I know. Like my nose.
I'm
started
sorry.
bleeding.
Do you guys not brand cattle?
This is nothing like branding cattle.
Whatever. It smells exactly
I
the same.
also, like, don't like just like stand in the way of
Except
I just
branding cattle, you get that, like, you inhale the smoke, like the smoke is in your face.
stand like upwind from them.
Do you stand there the whole time? I'm usually giving shots. I'm like weaving in and out, and I get hit in the face with all the smoke and have to breathe it in all the time.
I have to hold them, so it's
Yeah, so you're
I'll
getting
get
shot with
Smoke blowing
smoke
in my
all the
face,
time.
I might as well put a cigarette in my mouth.
Complaining, whatever. All right. Okay. When a guitar string is plucked, it vibrates with a frequency of, they give me the equation. That's exciting. F equals frequency equals 200 square root of t. What does t stand for?
That's not
The-
something.
What?
What? What are we talking about?
Tension.
Tension. F is measured in vibrations per second, and the tension is measured in pounds. Interesting. Find the rate of change of F. What are we trying to find? df dt. Find df dt when t is 4 and when t is 9. So we're going to have two different answers. Given t equals 4, given t equals 9. Okay.
This one's easy.
Is it?
Maybe not. Wait,
Do
no,
we have a
because-
dt dt?
Wait, what is the t again?
Well, the derivative of f would be df dt.
Yep. Okay, so let's do our derivative and let's see what we're missing here. We're df dt is this guy. This, I'm going to write this as t to the 1/2 power. Yeah? Okay.
So you need 100.
Pull that guy down in front. So that's 100. T to the negative 1/2 times dt dt. Oop, d capital T dt. And dt dt does not cancel out, right? Because we're different t's. One's time, one's tension. Okay. Right? Okay. So this guy, if I fix him, df dt is equal to 100 over the square root of t. dt dt. Oh, dt dt. Okay. We're trying to find df dt.
We don't have dt dt.
I know. We don't have dt dt.
What is that like? When it's this, so
The
it's
rate.
equal.
Okay, dt dt is the rate at which the tension changes with respect to time.
Do we not have enough information?
I think that we do, except I think dt dt is going to be 1. Because the guitar string is not going to change tension over time unless it's sitting there for years and it's starting, like the string's starting to loosen, true? The guitar string will stay the same tension no matter what when you pluck it, like the tension stays until you tighten the tension, right? So I think that's a constant now. Now I plug 1 in for that. Possibly? Yeah, I think so.
Seems like our only option, honestly.
I know, that is our only option. Either that or we're not given enough information. I don't know. Maybe I didn't give you enough information. Let me look at the book. I pulled this question out of the book. Maybe I'm forgetting something. If they don't give it to us, it has to be 1. Because it's not going to change. It just stays a constant. Zoop. Let's see. We're doing guitar strings. Review exercises. That's not what I want.
Hey Billy, guess what's for lunch today?
Freaky fries.
Close.
Is it schlop or cold?
Close. Straight up the Hamburglar on a bun.
Oh yeah.
Oh, related rates right here.
Oh, I need to go get money on my car so I can buy seconds because I'm actually starving like right now. Like my tummy's growling.
Jan might add on for the election thing.
I don't see where this came from.
It was so literal.
Thin air.
He was just like, he got so mad at the ladies talking about it.
Whatever. All right, we're gonna plug 1 in.
He was talking like,
Like beefing with the TV. 'cause
Yeah.
he has it on
Yeah,
the
we're gonna
local
plug it in.
channel.
Okay, so if t is 4 in part A. In part A, if t is 4, I plug 4 in, and you get the square root of 4, which is 2, and 100 divided by 2 is 50. And we're talking about df dt, so the frequency. The frequency is in what per what? the rate of change of F. Yeah, vibrations per second.
What's pounds then?
Pounds is the tension,
We don't care.
but we don't care about that. Okay, if we plug 9 in, the square root of 9 is 3, and the 100 divided by 3 is 33 and a third vibrations per second. Okay. We might have been missing a constant there in my explanation, but I don't know. I can't find the problem. I'll see if I can find it. Okay, good. All right.
Hold on.
Hold on, he says.
Okay.
I think it's 1 because the tension is not going to change over time unless you change it, right? Like the string doesn't become looser when you pluck it. It's still going to be the same tension, right?
It'll be under. I don't know what they're talking about, like, because when you when you pluck it, you move it, and then it's under more tension.
No. It's still under the same tension when you pluck it. The tension of the string is the same regardless of whether it's vibrating or still. The tension is
But
the
when you
same.
pull it down,
No.
like in the
No.
center,
No. That's the frequency changed.
the frequency change.
Mm-hmm.
Like
tension does not change.
Not like mid pluck.
No.
As
No,
I'm
that does
moving
not change the tension.
As I'm moving
No.
it down.
I understand what you're saying. I know what you're saying.
and
That's
there's
not how it works.
There's a pivot in the middle.
That doesn't make the string
It's
tighter.
making the distance.
That's not making the string
it's
tighter.
Increasing the distance that the string has
I don't
to
care.
travel.
I don't care. That's not
Therefore, it's
changing the
under more
tension.
tension.
No, it's not under more tension.
Yeah.
No.
How else would it be?
No.
What do you mean?
No. It's not under more tension when you
If
plug
there's
it.
a string
I don't think so.
and I pull down in the middle.
Right. It has more,
Is there
what
a
do they
ter-
say?
Am I missing
It
a
has
term?
more potential energy at that point.
What?
Because it's getting ready to vibrate. Yeah, it has more potential energy at that point.
It seems
Sure.
like the tensions are rising.
I don't think so. No, the tension is not. No, the tension is the same.
I don't know.
No.
Hmm.
Right. It's the same thing with a sewing machine.
Oh my!
You set the tension on a sewing machine.
Did you
Tension-
not break a sewing machine?
I did not. I fixed a sewing machine. I didn't break anything. There's 3 sewing machines and I fixed one. And the other 2 are screwed. So, on a sewing machine, most of the time you set the tension to 3.5, right? Okay, I set.
Tension on a sewing
I set the tension to 3.5. So if I am not sewing, the tension is at 3.5. If I am sewing, the tension is still at 3.5. True?
Okay, I don't know.
It's the same.
I don't know how
No.
a sewing machine works.
No, it's exactly okay. You push the button on the
Well,
foot
I
and
press
it
the
goes.
pedal and
It
it goes.
goes like that, like the vibrations of a dang cord string, whatever. It would be the same thing as a sewing machine. This tension on a sewing machine is 3.5 when I'm
3.5 what?
not pushing the pedal, and 3.5 when I am pushing the pedal. 3.5
Just 3.5.
pounds of force or tension. Yeah. Okay. All right. Moving on. Let's go to the front.
No.
Let's go to the front. We got a lot to do yet. Do you want to start at the top or start at the bottom? Would you rather do derivatives of exponential functions or implicit today?
Ooh, derivative of each x.
Would you rather do derivatives of exponential functions or implicit?
1,000 votes.
Let's just keep working backwards. Okay.
Really don't want to do either one, but
Sure. Okay, derivatives of exponential functions. You guys are going to have to grab your cheat sheet. I need to make you one sheet that has all of them on there. Yeah, true? Exponential functions. Okay, how do I take the derivative of e, let's start at the top, e to the 3x minus 2? What is the derivative of e to the 3? What's the derivative of y, by the way?
UIDX.
dy dx or just y prime or whatever we want to call it, right? Okay. What's the derivative of e to the 3x minus 1?
3x.
E to the 3x minus 1 times
3.
3. So can I do this? Like that? Can I do that? That's his derivative. Okay, let's work our way. I'm going to go down to 15 because I'm going to have to look up the rule for 14. If I go down to 15, what do I have to do there?
So here you basically
What do I have to do on 15?
3x squared.
Product rule. I have to do product rule. What's the derivative of y? We'll call it y prime. Sure, whatever. F prime g plus g prime f. What's f prime?
3x squared.
3x squared times g is just e to the x plus, what's the derivative of g? What's the derivative of e to the x?
E to the x.
E to the x, right? Times 1, or just e to the x, right? Times f, which is x cubed. Anything else?
Nope.
I just don't know why I didn't write that farther down, because we can't put anything together, so it's good. That's your derivative. Interesting. Interesting. Now I need to cheat, because I don't have these rules memorized. You have the inverse ones? No, I need the inverse ones. I will put these all in one sheet for you, for derivatives.
Literally, I found this underground.
Actually, no.
I was wondering if you've heard of it. Here, listen.
No.
It's by, you heard, it's by the Larry.
Okay.
It's like Juice WRLD son or whatever.
Okay, all right. Okay, stop. All right. This is what it says for the derivative of inverse tangent. Okay, so we've got inverse tangent of x cubed. All right. This is the derivative. Go. What do we got?
So basically, you gotta go
1 over 1 plus.
3x squared.
No. What's u squared going to be?
X cubed squared.
X cubed squared, which is x to the 6. Can I just do that?
No.
Times du dx. What's that?
The derivative.
Yep.
Of that guy.
Yep,
3x
which is
squared.
3x squared. Okay, now I'm going to just push him on the top. 3x squared over 1 plus x cubed. Or x to the 6, I mean. Does that work? That's inverse tangent. His derivative.
Should I write that down?
What?
That,
What?
du dx.
This right here?
Yeah.
No, I'm going to give it to you in one of these. I'll give you one of those. You don't have to memorize that. I'll give you one for that and for like these all up here. Okay. 7 to the x power. I don't remember this one either. This one says if you
7.
derivatives of no 3. Derivatives of exponentials. And this one says that if you have, okay, b to the x power is equal to b to the x ln b. That's his derivative. The derivative of b to the x power is b to the x ln b. Okay, what do you got? What will he be?
7.
What's the derivative of 7 to the x? What? Yeah, 7 to the x ln 7. That's his derivative. Okay, again, I will give you these rules and you just have to decipher them. Okay, 16. What's the, oh, by the way, this is y prime. Y prime equals, what's the derivative of e to the tangent x? E to the tangent x times, nope,
E.
the derivative of tangent x.
So is it cosine?
Cosine.
Derivative of tangent is secant squared,
Secant squared.
isn't it?
Yeah.
Okay, so you could flip those order, but I'm just going to leave them. Okay, e to whatever power is the same thing times the derivative of the exponent. Okay, how do I do 18? Y prime, by the way, equals, how do I do this? What's my approach
Bring
here?
in the front, the 3
Which is called the what?
exponent.
No. What method are you using? No. Yeah,
Chain.
you're using chain rule, right? 3 goes in the front. Roop. Inverse sine of x stays the same to the second power times the derivative of the inside. And the derivative of the inside, I will give that to you, is 1 over the square root of 1 minus u squared. But what is u? X. So I don't have to, like, do anything weird. Okay. That is that. Got it?
That's the answer.
Sure, unless you want to make anything else happen. Oh, we could. Y prime equals 3 inverse sine of x, whatever, to the second power over. That one, that looks a little fancier. Does that look fancier? Okay. Good. Okay, we will stop there. Tomorrow, I'm going to be gone. We have to do 1 through 12. That is it. How would you like me to do that? Do you want me just to let you work? Would you rather have me videotape it and do them with you, just kind of like I'm doing now?
Yeah.
Yeah?
Yeah.
Okay.
I'm not gonna lie. I don't know how to do implicit differentiation.
Do you want me to pause for 30 seconds in between each one so you can go ahead of me?
We can pause.
We could pause it.
You can pause it?
That's what the
You
video-
will pause it?
Like a video, you can pause button.
Okay. Will you do that, though?
Well, I mean,
Yeah.
if you want to, you
All
can
right,
sit
sure.
there for 30 seconds and twiddle your thumbs.
That's true. I don't want to do that every time. That's true. Okay. You pause. You pause it. Somebody be in charge of controlling this. And there's that. All right. Goodbye, Daniel.